very much. So I will be talking about comparing patent claims to other text, which could be a description from a patent, as well as searching. So I'd like to use that patent claim to search, where I'd like to find documents that contain all of the elements of that patent claim. In terms of data, I'm starting with the EPO search reports. Go to that raw data and then retrieve back all the documents that are cited, including USPTO. And I'm using the X and A that were previously mentioned. Those are annotated. The X negates the novelty. The A is relevant but doesn't negate. And the key thing is that the search reports, they tell you which paragraphs or which claims, which figures, etc., are relevant to each claim. So I don't have to use the whole document that's cited. I use just the parts that are relevant. And I use that to train a model, which I'll talk to you about on the next slide. There are a few results here that people have published in one way or another on this X versus A. Can I distinguish? Is the X relevant? Which one is the most relevant? And so what you see, and since it's binary, if you just do random, you'd be at 50%. So on this hard task, people are a little bit over up to 58% here. And there's the easy task, which is just distinguish between the X and the random, where people have published 58%. All right, so the first thing I'll talk to you about is building a custom LLM and two ways to use that. And so I use contrastive learning. I use the claim embedded into a feature space, which I'm embedding into a feature space, and I use the cited X document as a positive and the A document as a negative. But because of some characteristics, I also want to use that X as a negative, so I use that same X as a negative for some other claim and use the cited A as the positive. So that's how I train it. The chunks, I'm using the full text, but I'm always using only the chunks that are actually cited. That includes claims, it includes description, abstract, everything else. All right, so now I have my model, and what that model is doing is it's mapping a full claim to some chunk. So here are two different ways to use it. So the first one is just compute the maximum. So I have my claim, now I can compare it to chunks of a target document, where I have to chunk the target document, and then I just say, hey, the chunk that has the highest cosine similarity is going to give me the similarity of that whole document to that claim. The next one is saying, we have these elements, and maybe I can represent an element in just a paragraph. Instead of the big chunk that contains multiple paragraphs, I'll try to just compare elements to paragraphs using that same model. So I can do that, and then I can aggregate across those element by paragraph comparisons to try to get a document to claim comparison. And so here you have the results for both of those. So we're in the 60+% range, so definitely some improvement. And when we go to that easy task, we're at 99.6. That's up from 98%. So that's pretty darn good. But, so we look at, okay, I can use these chunks that have multiple paragraphs and compare them to a claim. I can use these paragraphs and compare them to a claim element. What about if I just ask GPT-4 and just say, hey, which of these patents is more relevant to this claim? Tell me, A or B. And there's some numerical results up there. And so the first one is, if I just ask GPT-4 that question, GPT-4 has access to all this patent data. And so GPT-4 comes back with an answer, and it turns out it's 53% right. So it's worse than all the things we showed before. But it's super confident about it. It's very eloquent, great explanation. And the next thing I noticed is that it often provides the first thing. If I said, is it more similar to document A or document B? It says document A. If I flip them and say, is it more similar to document B or document A? It says document B. And it explains it really well. So
sounds like it's rationalizing.
It's rationalizing, but there are various theories that just explain what is reason, and this is a counterexample to reason. So if I ask you, hey, what's heavier, the chair or the projector? You should reason about it and say, well, I think the projector's heavier, or whatever it is. If I flip it, you won't change your mind. So this is really proving, in a way, and there are many ways to prove it, but it's really another demonstration that these LLMs, they don't think, they don't reason. And that has a lot of implications. Yet people think that they're intelligent. So it even calls into question, what is the relationship between language and thinking? What's the relationship between language and intelligence? I'd love to talk about that a little bit also. I will say that when we upload the full text of the documents, then GPT-4 does pretty well. It's up to 59%, and that's a small set, so it's within the margin of error of certainly 60 or low 60s. So it's doing pretty well. All right, so conclusions. So for the custom model part is implemented using cosine distance, so I'm able to take millions of documents and throw them into a vector database and do approximate nearest neighbor search, and I can search them in sub-second and get back the top 500 results or whatever it is, and then I can re-rank, and I can have a real-time demo that's doing semantic search across basically all patents. Very practical, it exists, I can show you. Another conclusion is, hey, LLMs don't think. That's pretty exciting. So if we're worried about them taking over the world, I can promise you they won't, because they don't even think. They don't have any published. But yeah, super eager to collaborate. So I'm with a tiny company that has basically no money, and I would love to work with any of you guys. A number of you have talked about some similar things, and really look forward to speaking. Please do come by the poster.